con nuestro encuentro de ingenierías. Nuestro siguiente ponente es doctor en Economía por el Colegio de México y licenciado en Matemáticas por la Universidad Autónoma del Estado de México. Ha hecho estancias de investigación en Glasgow University, en Escocia, y en la Paris School of Economics, en Francia. Ha sido participante en eventos internacionales, como la Young Economics Meeting en Brno, en el 2016, la 21st I-Force Conference en Quebec, en el 2017, y la Social Choice and Welfare Meeting aquí en México en el 2022. Él ha estado interesado en teoría de juegos, diseño de mecanismos y la modelación matemática, y ha publicado artículos de investigación sobre la existencia y unicidad de soluciones a problemas económicos, así como el desarrollo de mecanismos de asignación en interacciones trilaterales. Es miembro del Sistema Nacional de Investigadores, en el nivel 1, ¿sí? Y es un gusto para mí presentar al doctor Damián Emilio Gibaja Romero, actualmente director del área de economías de nuestra universidad. El título de su plática es The Nash Equilibrium as a Direct Optimization Problem. ¿Sí? Un aplauso, por favor.
Bueno, buenos días a todos. Gracias por su asistencia. Okay, so I'm going to mix English with Spanish. I'm going to talk about the research that I do. So this talk is related to a working paper with David Cantala. But before to talk about the paper, I'm going to give you some basics to understand the general idea of the research. So I would like to start with three important questions. Do you know what is a game? Please raise your hands. Yes? Okay, the majority of people knows what is a game. Also, are you familiar with the assignment game? Okay, more or less. And finally, do you remember the intermediate value theorem? Okay, so these three questions are very, these three concepts are very important for the talk. So let me first introduce some basic notions about game theory. As Lorenzo said in the previous talk, well, game theory is the branch of mathematics that deals with problems where agents have conflicts. So we analyze decision-making when the actions that take other players impact the actions that we choose. And this is a very classical problem, the prisoner's dilemma in game theory. Have you watched this movie? Do you recognize these pictures? Where are they from? Yeah, that's correct. These pictures are from The Dark Knight, the movie where the Joker and Batman fight each other. And if you remember, at the end of the movie, the Joker puts two bombs in two ships, and the Joker tries to develop some interaction between the two ships that recalls you the prisoner's dilemma. In that sense, you have two kind of players, the ship with normal people and the ship with the people from jail. And the actions that the players can take are people can blow up the ship of the jail people and don't. The people can choose between these two actions. Also, the jail people can choose between two actions, blow up and don't. So we have a conflict between the two ships. And this conflict is related to a payoff matrix that we can summarize in this place. You have the actions of both players, and we can assume these payoffs. For example, we can consider that both players win -1 if they blew up the ships because they lose their lives. Also, we can assume that if the J people chooses don't blow up the other ship, the people wins too because these people survive and blew up the other ship, while the jail people, well, they die and they also lose the opportunity to blow up the other ship, and so on. We can define that if people and prisoners don't blow the other ships, well, they get 0 because if you remember the movie, the Joker has another device to blow up both ships. So this is a game. What normal people choose impact the result from jail people, and also what jail people do impact the result that normal people get. So here we can summarize the basic elements of game theory: players, actions, and payoffs. So, and now we can think in another interactions, for example, the assignment game. If you remember, the assignment game is related to the assignment problem, which is very basic for operations research. You have machinery and you are going to assign such a machinery to develop some task. For example, we have 4 machines and 4 tasks, and we are searching for an assignment that minimizes the cost of performing all the activities in this problem. So the basic assignment problem starts with machines and tasks. However, we can generalize this problem in a situation where in both sides of the problem, we have people with preferences. For example, if you want to get married, this is an assignment problem where boys search for a girl or vice versa. And in this case, this assignment problem is more like a game because here machines are indifferent with tasks. There is no distinction because we only need to spend gasoline or maybe time to do some of the activities. However, in this case, it is important who gets married with whom. So it is a little complicated to study this kind of problems because boys have preferences over girls and girls have preferences over boys. So the assignment game is the interaction that arises when we have this kind of structure. So we need to find some solution to understand the decision making that both kind of players do in this game. So this is a very general introduction about the assignment game, but later I'm going to talk more in depth about the structure that I am researching. So, and finally, if you remember the intermediate value theorem, we have a very basic theorem when we only have a continuous function on a closed interval. If you assume that the image of f in the point A is strictly lesser than the image of f in the point B, we can find a point C such that there is here is a typo. Here, instead of C, I should put U. So you can find a value in the closed interval that coincides with the value of U. So in this case, the intermediate value theorem allows to solve some kind of equations if we have a continuous function and also if we have this relationship. So we can find a point in the domain that satisfies a value of the image. Okay, so this theorem is going to be useful for the next part of the talk, and also it is important to remember the intermediate value theorems for integrals. In the same sense, if we have a continuous function on a closed interval AB, we can find a point C where the image is equal to the average value of the function. Okay, so we can simplify an integral in this sense. Okay, so we can generalize the previous theorem by considering by considering improper integrals. In this case, if we have an upper and lower bounded function, and we have a right continuous function g, we can simplify the integral of the product between h and j by considering an average value of h, which we call mu. So if you want to simplify the product of the integral of the product of two functions, you can avoid using the function h by finding the average mu. So we are going to use this theorem, the mean value theorem for improper integrals, to simplify the searching of a Nash equilibrium in the next part of the talk. Okay? So, any questions? No? Okay. So now, the name of the working paper is Uniqueness of Equilibrium Prices in an Assignment Game. So, as you can see in the Dark Knight game, the outcome of each player depends on the actions of the other players. So here I put in green the dominant strategy of normal people, and in red the dominant strategy of Yale. As you can see in this matrix, you observe that blowing up the ships is the Nash equilibrium of the game. Okay, but as I told you before, to compute this solution, we need to look out for the decision that the other players do. Okay, so in a normal game, we need to analyze all the alternatives that normal people have when J people also is going to make a decision. So now, in this working paper with David Cantala from El Colegio de México, we analyze some conditions to guarantee the uniqueness of the Nash equilibrium. Also, it is typical that solutions in this kind of problems are not unique. Think again in the game between boys and girls. How many matches can you do in this situation? So you can imagine many ways to match a boy with a girl. So in the Nash equilibrium, we find that there exist several possibilities to match boys and girls. This is a problem because if we have multiplicity, it is not clear the predictions that we can do. So we try to simplify such a problem by researching on the conditions that the game should satisfy to guarantee uniqueness. So this is the outline of the paper. We have the problem, the model, the equilibrium analysis. I'm going to describe how sellers, in the context of the paper, instead of calling players as boys and girls, we call them buyers and sellers. And we are going to describe the probability of selling, which is the basis to find the condition to guarantee uniqueness. Our main results and a simple example to illustrate the results of the paper. Okay, so our motivation is the assignment game. We have agents that supply and demand only one indivisible good. This game was introduced by Shapley and Shubik in 1971. And in this game, since we have indivisible goods, the outcome is related to prices. This is a very interesting problem because when you have indivisible goods, you lost convexity. And if you lose convexity, you cannot apply the typical tools of mathematics to find the optimal prices. Okay, so they try to maximize the utility that both agents get when you don't have the possibility to compute the first derivative and later the second derivative. So in this case, Sheplin-Shubik introduced a combinatorial assignment process to find the best prices. However, although they solve the problem to find the best prices, the assignment that they proposed also generates a multiplicity of competitive equilibria. After the paper of 1971, Shapley and Scarf also analyzed the same problem in 1974. Quincy introduced a condition over the amount of money. The Mensch and Gale tried to modify the mechanism to get the match between buyers and sellers, and so on. There are many papers that have studied the assignment game in order to improve the solution that we get. However, in all cases, as far as we know, they get multiple equilibrium. So if we have multiple equilibriums, we are in problems. The main critique about this approach is the lack of sensitivity. The results are insensitive in the sense that we cannot change exogenous variables to analyze what is happening with the equilibrium strategies when the exogenous factors change. So the main critique about this approach is the fact that we get insensitivity. So we try to find some conditions to guarantee the existence of a unique equilibrium. So we propose a Bayesian game, which is a two-stage game where the nature draws valuations. Agents observe their own valuation about the goods that are in that are in the market, and after that, sellers set prices, and we consider a more simple mechanism that Shaplin-Shubik, in which each good is sold to a buyer for whom it maximizes her surplus. So we are thinking in an assignment process that is more direct. Also, we assume that in this game, buyers are not strategic, only sellers try to set the price that maximize their benefit. And well, our main result is a uniqueness condition, which is related with the inverse hazard rate. Have you listened about the inverse hazard rate? Maybe Arturo? More or less? Someone else? People from quality? No? Well, the inverse hazard rate is related to the failure rate in engineering processes. So, well, our uniqueness condition is based on this ratio. And also, well, we are going to use the assumptions that the intermediate value theorem considers to get the uniqueness condition, okay? So, the related papers are those that analyze reverse auctions. The fact that we consider that sellers establish their price has similarities with reverse auctions. If you remember, in a normal auction, the agents that put prices are the buyers. In these games, we consider the opposite case. Sellers are the ones that put prices, and sellers wait for a buyer to buy their good. So in this sense, we are relating the assignment game with a reverse auction. Also, these kind of problems have, these kind of models have a lot of applications in procurement, when you are trying to assign some public goods or some public services to private enterprises, you need to do this kind of process, of mechanism. So we find reverse actions in the electricity markets because we are searching for providers of electricity in the short, medium, and long run. Also, for transition to renewable energy, there are some permits that allow private enterprises to produce energy. So the government follows the reasoning behind a reverse action. However, in these papers, they only consider many sellers and only one buyer, or only one seller and many buyers. In other words, in our paper, we are trying to generalize this literature by considering many sellers and many buyers. Yes, because since the immediate application of reverse action is procurement, we only, typically in procurement, we only have in one side of the market one player, which is the government. Also, our paper is not new concerning the application of the intermediate value theorem. Also, in the action theory, we find that people use the intermediate value theorem to simplify the mechanism and to avoid assumptions related to symmetric linear behavior. One of the main difficulties of finding a Nash equilibrium is the fact that it is an NP-hard problem. So you have to simplify or you have to impose some strong assumptions related to the behavior of the other players. For example, symmetric behavior, because if you don't do it, finding a Nash equilibrium tends to be a lot. Well, the complexity increases a lot when you don't impose this kind of assumptions. Okay, so in our paper we avoid the symmetric linear behavior. We by using the intermediate value theorem, we can analyze the decisions of players by considering a more general behavior, which we think it is well, it is a good contribution because, well, we have a more general set of behaviors. And, well, we also simplify the best response correspondence. Okay? And also, we have other papers that are related with us. As I told you before, the main motivation of our paper is the possibility of doing comparative statistics, comparison of equilibrium when exogenous parameters change. Indeed, when you have multiple equilibria, there are papers that analyze some kind of comparative statics. For example, Alkan, Manch and Gale, Tadenuma, Thompson, and Svensson do an artificial comparative statics by considering the whole structure of the set of equilibria. So they try to move all equilibria in the same direction by modifying the external factors. However, well, they impose a lot of restrictions, and it is not possible on their approach to analyze the impact of exogenous variables into only one equilibrium. In this case, you need to change all the, well, you need to move the set of all equilibrium, okay? And concerning uniqueness, you can find, if you are interested in this kind of literature, you can find papers that analyze in different contexts some conditions to get unique equilibrium in rent-seeking games, Cournot games, weighted potential games, and so on. It is a problem, well, an interesting problem, how to reach a unique solution. In general, conditions depend on the structure of the game. The conditions that we find in our paper are different from the conditions that these authors find for this kind of games. Okay, so there is more literature about uniqueness. We are not the only ones. Okay, and well, our main contributions are, I told you before, we establish conditions to guarantee the existence of a unique equilibrium price vector in the assignment game. And we also can provide a closed form solution that allows performing some comparative statics. So I will give you an example concerning this closed form solution, which is a formula. So formally, what is the model? We have a set of sellers, M sellers. Each seller has an initial endowment composed by an amount of money and an indivisible good. We assume that sellers at the beginning of the game, since there are no previous exchanges, sellers have, when the game starts, 0 money, and sellers have one and only one indivisible good. Okay. Also, sellers have a valuation of her own good. This is private information, which we denote as BJ. And concerning the buyers, we consider M buyers. The cardinality of sellers is not necessarily the same that the cardinality of buyers. So N and M can be different. And in contrast, buyers have an initial endowment composed of an amount of money omega, and buyers don't have a good. They are waiting for the game to get a good that they prefer. And we assume that buyers value each good in the market. They observe all goods, and there is a valuation, Bij, that summarizes the value that buyer I gives to the good of seller Sj. Okay, so the type of a buyer is a vector of valuations that summarizes all the valuations that the buyer has about all the goods in the market. So also this is private information, and concerning the state of the market, we have a very large vector that comprises the seller's valuations together with the buyer's vectors of valuations. So we consider that this state of the market is drawn by following a probability distribution F, which is of common knowledge. Okay, so these are the basic elements of our game: sellers, buyers, and a state which introduces some kind of uncertainty. Okay, and now if you want to analyze the assignment game, we need to induce the preferences that buyers have over goods and that sellers have over selling or not selling their goods. So we consider, as it is classical in this kind of literature, a quasi-linear utility function, which is the sum between the good that they get and the valuation of the good that they get. Okay, so if a buyer buys a good, the utility that the buyer gets is this. If the buyer does not buy a good, the utility that the buyer gets is only the money that the buyer has at the beginning. And concerning the seller's preferences, I think I have a typo. Let me check. Yes, this is sellers and this is buyers, because yes, Yes, here I have a typo, sorry. Well, in words, sellers get money and buyers get money and a good, because they use money to pay the transaction between the exchanging of a good. Okay, so maybe in the next slide it will be more clear, because I develop in detail the expected utility of sellers. So what is an assignment? So we need to match sellers with buyers. What is an assignment in this context? Well, it is a map from the union of both sets to the set of money and the set of goods. We identify not having a good by using the empty set. It is possible that buyers don't buy a good, and also it is possible that at the end of the game, sellers sell their good, and well, they remain with no good, which is denoted by the empty set. So the assignment provides an amount of money and a good, okay? And we also impose some constraints in the assignment, because we want to have some desirable properties, such as feasibility. An assignment is feasible when the money that we allocate in all players does not exceed the money that buyers have. Okay, so we cannot get more money than the money that we already have in the market. And also we ask for the assignment that concerning the allocation of the good, the function is injective. In other words, we cannot assign a good to more than one agent if the allocation is the same for two agents R and R prime, then these agents are also the same. This is the meaning of an injective function. And as before, we consider that if some good is assigned, is because there exists a player that gets the good. Okay, so we cannot assign an invisible good to the empty set. We need that someone, a buyer or a seller, gets the good. Okay, so this is a technical property only to guarantee that goods are assigned between buyers and sellers, and we cannot assign a good to more than one agent, okay? And well, also it is desirable that the assignment satisfies individual rationality, which means that the utility of the assignment that each agent gets is larger than the utility that they get with the initial endowment, okay? So if they play the game, it is a rational assumption that the allocation mechanism will be individually rational. So we want to be better when we participate in this kind of interaction than when we remain outside of the market. Okay, so individual rationality means that. And as I told you before, the game is a two-stage game. The nature draws sellers and buyers' valuations. Sellers in the second stage set the price of their good. And the assignment mechanism is a sequential process that assigns goods whenever there are maximals for some buyer E, and when we are searching for maximal, the minimum of maximal is related to the surplus. Remember, buyers have a valuation about each good, and buyers have to pay a price to get the goods. So the mechanism look at the surpluses of each buyer, which is the difference between the valuation, which can be interpreted as a gain, and the price that they pay, which can be interpreted as the cost. Okay, so this is the surplus of buyer I, sorry. Okay, so and the mechanism assigns in a sequential manner all goods only if the goods are maximal. In case of ties, the ties are randomly, well, we broke ties in a random manner, okay? So, any questions about the basics of the model? No? It is clear? More or less? So we have buyers, sellers, they want to exchange a good, and sellers set prices to realize the exchanges within the game, okay? So as you can imagine, sellers to set prices, we need to establish the seller's optimization problem. What is the rule that they follow to set a price? Well, before to establish the optimization problem, since valuations are private information, we don't have a certainty concerning our utilities. We need to look out expected utilities because there is a probability of selling, but also there is a probability of not selling, okay? So remember, the fact that buyers have valuations over all the sets of goods means that maybe if the price is too large, the buyer is not interested in the good, okay? So the game relies on the fact that not all buyers want to buy a good, okay? So we have an expected utility. A seller gains PJ, so, sellers gain the price that they set in case of selling. But if a seller does not sell her good, seller gains the valuation because the seller remains with the good that she has. And this is the expected utility. We can simplify this expression by making a linear transformation. Indeed, we try to avoid this probability of not selling by taking the difference between PJ and BJ. So if you take the difference, in this case, BJ minus BJ is 0. So you simplify the function. We only need to take care about the net profit that the seller gets and the probability of selling. So here we have PJ minus BJ, okay? So the seller's problem is to maximize this expected utility function. And now we need to know how to compute the probability of selling. Do you have any idea about the probability of selling? Can you imagine how to compute this probability? Remember, we have a game, we have different sellers, we have different buyers and different goods. So this probability depends on the behavior of the other agents in the market. So we need to explain in detail how to compute this probability. So after that sellers set the price, all buyers build a preference relations over the set of goods, and we have the most preferred good, the second preferred good, the third preferred good, and so on. So let me explain in detail how to compute this probability of selling. Given a price vector P, we denote by SGK as the event where the good Sj is one of the K most preferred good of buyer I. And if we have a situation where, well, for any result, well, for any instance in the event, we can see that buyer I gets the largest surplus, which is denoted by CJIK. So if a buyer buys a good that lies in this event, well, the buyer gets her K layers surplus, which, well, as I told you before, is the difference between the valuation and the price. Okay, this is a gain and this is a cost. So the surplus is the net profit that the buyer I gets after buying the good. So since we consider this mechanism to assign the goods between buyers and sellers, it is possible that when a seller sells her good, it is possible that a buyer how do you explain this? I'm going to say it in Spanish because it is easier. So, si un vendedor vende su bien, puede ser que el comprador lo considere como el mejor, el segundo mejor, el tercer mejor, así hasta el peor. So, in this case, we order the events from the best good that a buyer I can get to the worst good than the buyer I can get. Okay? So, if you are familiar with this kind of probabilistic events, we can demonstrate that this is a partition for the more general event, which is the event of selling the goods. And if we impose some independent, well, if we assume that events are independent, we can disclose the probability of selling as the sum of the probability that some buyer I gets the best, the second best, and so on. Okay, so the probability of selling is equal to the sum of these smaller events. And now we haven't finished to compute the probability, since we can simplify the probability of selling as this sum, but the next step is, well, how do we compute the probability of these smaller events? As I told you before, we have an order among the set of surpluses. We can order these surpluses from the best to the worst. So we have an order statistics family of a sample that considers the difference between the valuation and the price that buyers have to pay for a good. And we can compute the previous probabilities by following these rules, which something of you know that the probability is equal to an integral. Okay, but in this case, since we have order statistics, well, we have to split the probability into, well, we have to find the joint probability function, because in this sample, the random variables are the transformation between this random variable and this random variable. So if we want to compute the probability in a direct manner, we need to do a lot of transformations, which, as you can see, is very tired, because we have the integrals concerning the joint probability function related to the order statistics. But here you can see a very simple distribution function, which is related to the probability, well, concerning the valuation that buyer I has over a good J. So here we have a marginal distribution, and in this part we have a joint distribution function. So this is very complicated if we want to compute the probability in a direct manner. That is the reason why we introduced the intermediate value theorem to simplify the previous integral. So to avoid the previous calculations, well, we assume, well, we don't need to assume an extra condition, because probability distribution functions satisfies the conditions that the intermediate value theorem needs. As you remember, we need an upper and lower bounded function. Also, we need that functions are right continuous. Well, we assume that other sellers' behavior is differentiable over the set of valuations. Okay, so when you apply the intermediate value theorem, you can simplify this integral by finding some constants, mu1, mu2, mu3, and so on. These constants are the average of the distribution function capital Fc. And with the intermediate value theorem, we only have to compute this term, which is the complementary event concerning the probability that valuation is lower than the price that the seller J sets. Okay, so notice this is a very important result, because notice that we simplify these expressions in this simple calculation. Okay, so it is more easy to analyze the expected utility of sellers by considering these probabilities. Okay, if you want to interpret these probabilities and you want to know the meaning of these constants, we find that these constants are related with the conditional probability of selling the good for some buyer that considers the good as the top, as the second, and so on. Okay, so these constants mu are related to a conditional probability. Okay, so with the previous work that we have done, we can develop the expected utility of sellers. So as before, remember, sellers maximize their expected utility, which is equal to the difference between the price and the valuation. And here we have the probability of selling, which is this more simple expression multiplied by m. This m is related to the constants that provide us the intermediate value theorem. So here we have a constant, and we can simplify the calculation of the best response correspondence. If we want to maximize the expected utility, we need to compute the first order condition. In other words, we have to solve the first derivative equal to 0. We need to find the zeros of this equation. And when you develop the derivative of this expression, you find this, and you can write this expression as this. Okay, so the intermediate value theorem allows us to delete this constant. It is not necessary since it is a constant, but it is really important because if you observe these equations, you don't have the prices of other sellers. Indeed, this is a very interesting result because we transform a game theoretical optimization process into a direct optimization process. In this process, we find that it is not necessary for seller J to consider the actions of other sellers. So in terms of the game in the movie, in this case, normal people do not need to look at the decisions of the prisoneres, okay? So, well, for game theoretical people, this is a very counterintuitive result, because the classical approach suggests that when you look out for the best response correspondent, it is typical that you see the actions of other players. In this case, the intermediate value theorem allows to avoid imposing additional assumption concerning other sellers. Okay, so we can rewrite the previous expression. The prices are the solution of this equation. The best response correspondence is described by this, where we note that this expression is the reverse hazard rate. So do you remember the meaning of the normal hazard rate? ¿Sí? Sorry. The direct hazard rate measures the rate of change. Okay, so the hazard rate summarizes the risks of a change in the problem, and well, the reverse hazard rate, it is more difficult to explain, but can be understood as a conditional measure of risk in decision making. Okay, so as before, this is a very important remark. The reverse hazard rate that we find only depends on the probability distributions related to seller J. So again, all the searching for the best response of each seller is independent of other sellers' prices. Okay, and that is the reason why we can say that this assignment game is a direct optimization problem. We don't need to look out for the other players' actions to find the price that maximize the expected utility of sellers. Okay, so as you can imagine, this is a non-linear function, and if you want to solve a non-linear function, well, you can use some numerical methods like the Newton method, which is an iterative process to find the solution of a non-linear equation. You start with a guess, and after that, you iterate this formula to find a better solution. So at each step, the process is searching for a better solution, and it is possible to demonstrate that a root of any a root of a nonlinear equation is given by the limit of this process. Okay, so we use the Newton method to find the solution, and well, this method only serves to find roots, but we need to find a unique root. Okay, remember, we are interested on the uniqueness of prices. So in such a case, the Newton method converges to a unique solution when the nonlinear equation is described by a contraction. What is a contraction? Well, a contraction satisfies this inequality. In words, the difference the distance between the images is upper bounded by a constant by the distance between the points in the domain. So we are trying to to reduce the distances between images of the function to generate a contraction. Okay, this is called the Lipschitz constant, or also the Lipschitz conditions. It simplifies the behavior of the function because we operbounded by this linear difference, and well, this constant lies between 0 and 1. So our main result is this. If we have the conditions of the intermediate value theorem for improper integrals, plus the fact that the reverse hazard rate function is a contraction, we can guarantee the existence of a unique equilibrium. Okay, so here we have an example. You can consider that valuations are exponentially distributed. So we can consider the exponential distribution function where 1 divided by the parameter reflects the average of waiting times. And well, this function satisfies these two conditions. And as we can expect by the previous theorem, the equilibrium price is unique and is given by the valuation plus 1 over the parameter of the exponential distribution. So this is a very good result because we can write equilibrium prices as a closed form solution that allows us to make some comparative statics, even when you impose these conditions to these expressions. You also can develop some comparative statics to analyze the sensitivity of equilibrium when exogenous parameters change. But well, we decided to include the exponential distribution function because, well, the result is very simple and it's very clean. And as I told you at the beginning of the talk, one of the main critiques around the assignment game is the fact that we cannot make a sensitive analysis. If you impose the previous conditions and you find a unique equilibrium price, you can take the relationship with exogenous parameters like the valuation of sellers and the parameter of the distribution. In this case, and well, this is a very obvious relationship. The price increases as the valuation of the seller also increases. And here we have that the price decreases as the parameter increases. Okay, the first one can be stated in a very general way. We don't need to establish a particular distribution function. As I told you before, if you analyze this, if you take the derivative concerning the valuation of seller J, you can get the same result. And the second result, well, depends on the parameters of the distribution. So since distributions are different, well, we can have different relationships here depending on the distribution. Okay, and also, well, we can given the properties of the exponential distribution, we can extend the problem to an environment where valuations are not identically distributed. For example, buyers and sellers may have a different waiting time parameter. So, but well, we can change this, and we can consider this scenario, but also we can get a unique equilibrium. Okay, so well, we believe that we get this result because the exponential distribution has nice properties, and we also believe that this is the only one that that provides an inverse hazard rate that is a contraction map, but well, it is a next paper to look out for other features of the distributions that guarantee the previous set of assumptions. Okay, and if you have doubts concerning if there is an instance where the theorem does not hold, well, here you can find a distribution function that does not satisfy the contraction mapping assumptions. And well, if you develop in detail the expected utility function, well, you find first an equation of order 4. So it is clear that in this case, we are not going to get a unique price equilibrium. So it is a sufficient condition to look out for a contracting reverse hazard rate. Okay, and well, finally, some conclusions. As I told you before, we generalize previous works concerning the reverse actions procurement theory. We provide a model that deals with several buyers and several sellers. Also, well, it is not common that these people look out for uniqueness condition. They also tend to have multiplicity in their models. So, well, we think that imposing the previous conditions may help to simplify the development of mechanisms to guarantee an efficient procurement process. And also, well, we provide other example where we can apply the intermediate value theorem, which can be very useful to simplify the analysis of bird responses in these conflict interactions. And well, we have the closed form solutions for the exponential case. So, well, thank you for your attendance. Any questions? No? ¿Dudas? Lorenzo? Well, the intuition is related to this part. Since we have a Bayesian environment, indeed, we can say that seller J is watching for the average. So seller J considers that other sellers are, yes. Seller J considers that other sellers behave like an average. Yes. Yes, the technical part is the fact that, well, we can simplify, we can avoid the surpluses given by the other prices. So we can get the average of those surpluses. Okay. Another question? No? ¿Seguros? Okay. Gracias.
Okay. Thanks. Damián Emilio.
Excellent
presentation.
Gracias. No, gracias a los organizadores. Bueno, gracias. No olviden visitar las otras actividades del área de matemáticas. A continuación sigue el taller de Pitágoras en los salones T. Si están interesados en ver aplicaciones de Pitágoras, en T250, T251 y 52, ahí estarán. O pueden ir a otras actividades del evento. Gracias a todos. Buen día.